Let's look at this problem. How many perfect cubes lie between these two numbers? 2 to 8 plus 1 and 2 to 18 plus 1, inclusive. So when we have a problem like this, how do we think about it? A natural thinking is if you know the specific numbers, then we can try it out. So let's say if we have two numbers, let's say from 1 to 100, and then how many cubes are there in this range? Then we can give it a try, right? Or we can find the lower bound and find the upper bound. And everything in between will be the perfect cubes. That's one way or a natural way to think about it. But in this particular problem, we have a range of something, an exponential plus 1, and an even bigger exponential plus 1. Then what is the difficult part in this problem? The difficult part in this problem are these two numbers or these two exponentials. They can be very large so that we couldn't complete the computation in a reasonable amount of time. Then let's check carefully with the exponentials and see if we can simplify the problem. Alright, let's look at the upper bound first. The upper bound is 2 to 18 plus 1. Let's put plus 1 aside and just look at this 2 to 18. Then you probably remember that when you learn the exponentials, there are some rules or formulas to calculate exponentials. For example, we can transform this 2 to 18 to 2 to 6 and then parentheses, cube from outside. Good. Then this is a perfect cube by itself, and that doesn't require a lot of computation about the exponentials. But the problem says it's inclusively. We only know that the first term is a perfect cube. Then how about this perfect cube plus 1? Can that be another perfect cube? The answer is no, it can't be. Because you think about this. You have one cube of a natural number. And then you have another cube, which is the very next one that is greater than this cube. Then it got to be n plus 1 cube, right? Then if you take a difference of these two cubes, so this quantity equals 3n squared plus 3n plus 1. Therefore, we know that as long as this n is not 0, and in our example, of course, that n is not 0, then this quantity will be much larger than 1. Therefore, this cube plus a 1 couldn't be the next cube. Then we know that the upper bound of a cube within this range got to be this number, 2 to 6, and then cube. And then we want to find the lower bound. A natural thinking about the lower bound is, okay, we applied an exponential rule with the upper bound. Can we do the same trick with the lower bound? We can give it a try, right? The lower bound is 2 to 8 plus 1. And can we make up a cube out of this 2 to 8, just like the trick we did here? So you give it a try, and then you realize that since this 8 is not a multiple of 3, you can't easily to convert it to a cube of an integer. Therefore, that is not a good option. We have to turn somewhere else and find a different way to estimate the lower bound. Then what is a better way? The one thing you should notice that this quantity itself, 2 to 8 plus 1, is not that large. It's not like this 2 to 18. For 2 to 18, you can't compute it, because we know that 2 to 10, that's already like 1,024, right? And then 2 to 18, that number would be super large. I don't know, maybe in hundreds of thousands, or even, I don't know, maybe millions. But no matter what, we can't do it in a reasonable amount of time. But for the 2 to 8, that's a different story. Since the exponential rules couldn't help here, let's just do it in the brute force and just do the direct way. And all because this number is not too large. Good. Then what is the quantity of this 2 to 8? So 2 to 8, we know that that's 256. And then plus 1. So you may wonder, how do you know this? Actually, when you prepare for the AMC tests, I always recommend you to remember all the exponentials from 1 to 10, at least to 10 of 2s or maybe of 3s, because these numbers are frequently used. But never mind if you didn't memorize that. You can just do this, right? You should at least know that 2 to 4th is 16, right? Then 2 to 8, then that's simply 2 to the 4th square, then that's 16 square. Then it's not difficult to get this number, 256. Plus 1, that equals 257. Good. Now our goal is to find a perfect cube that is right above this number, or in other words, slightly larger than this number, or maybe equal to this number, because here it's inclusive. Now let's give it a try. So what's a good starting point? Let's try, I don't know, let's just try some random numbers. How about 5? So 5 times 5 times 5. We know 5 square, that's 25. Then times 5, that gives you 125, right? So obviously this 5 cube is too small. How about 10? Then 10 cube will give us 1,000. Then that's too large. Good. Then we are confident that because this number is not any outrageous number, it got to be between 5 and 10. Okay, what shall we try next? Then let's try some number between or in the middle of these two quantities, 5 and 10. So let's try 7. So 7 squared equals 49. And then 49 times 7 gives 7 times 9, that's 63. We carry a 6. 4 times 7, that's 28. Plus 6, that's 34. 7 cube, this is 7 cube. 7 cube is greater than this number, than the lower bound. Okay, let's try one more. How about 6 cube? So 6 cube equals 6 squared, that's 36, times 6. That is 6, that's 36. Carry a 3. And 3, 6, that's 18 plus 3, that's 21. Good. So this number is less than 257. This is our lower bound. Lower bound. Right? And this number is less than 7 cube. That's here. Then we know the smallest perfect cube within this range is 7 cube. Therefore, all the perfect cubes between 7 cube and the 2 to 6 cube are within this range. Then how many of them are there? Then we have 2 to 6 minus 7 plus 1, right? So that's 2 to 6, that's 2 to 5, that's 32. 2 to 6, that's 64, minus 7 plus 1. That's 57 plus 1. That's 58. 58 is our answer. Let's look at the choices. Okay, E. E is our choice. If you like this video, please subscribe the channel and thumb up. If you have questions, please comment.